Hello again. From the College Uta page. The title of this lecture is Linear Programming Part 1. And please note this contains 2 low-stakes assessments. And as always, please be attentive learners while watching this video. By way of introduction, as discussed last class, tonight holds a AMATYC contest conflict for me, so we cannot meet in our regular fashion. But teaching and learning continues unabated through this content video and the associated assignments. This video lecture deals with another important linear algebra topic called linear programming, and again is an important application. And this will be the first of several video installments on this linear programming topic. And again, note, there are LSAs embedded in this video. Let's begin with some fundamentals. The graph of an inequality is the collection of all solutions to the inequality. And if you wanted to sketch the graph of an inequality, 3x minus 2y less than 6, you begin by sketching the boundary of the corresponding equation. And the graph of the equation separates the plane into 2 regions. In each region, either all points in the region are solutions to the inequality or no points are solutions. So you can determine whether the points in an entire region satisfy the inequality by simply testing one point in that region. Sometimes you'll be working with linear equalities that are less than or equal to, greater than or equal to. Now the graphs of each of these is a half plane lying on one side of the line ax plus by equals c. That's the boundary. When the line is dashed, the points on the line are not solutions of the inequality. And when the line is solid, the points are solutions to the inequality. The simplest linear inequalities are those corresponding to horizontal or vertical lines. Let's look at an example of this. So sketch the graph of each of these linear inequalities. X being bigger than or equal to minus 2 and y less than or equal to minus 3. I will give you a little bit of time to do this. Let's see how you did. So this is the region you should have gotten for x equal minus 2 is the dotted line, and for x being greater than minus 2, it is this region. For y less than or equal to minus 3, you have a solid line, and it's the blue shaded region. Let's have you do another example. Sketch the graph of x minus y less than 2. Please pause the video and give it a try. You should have had the line being dotted because it is a strict inequality, and you should have shaded above, and the test point that I used here was 0, 0. Let's look at another example. This time we have 3 inequalities, and we're looking for the real intersection of these. So we graph all of these and look where they intersect. Please pause the video and give it a go. Let's see how you... Okay, so this is the area that is common to all 3. Notice that 2 of the boundaries are dotted and 1 is solid. And again, it is important that you find these vertices. You'll see why in a bit. Now for the triangular region shown in the earlier example, each point of intersection of a pair of boundaries corresponds to a vertex. Now with a more complicated region, for example, this example down here, this boundary and this boundary intersect somewhere that's not common to the intersection of all the regions. So with more complicated regions, 2 border lines can intersect at a point that is not a vertex of the region. So determine which points of intersection are actually vertices of the region, sketch the region, and look at your sketch. Now, when solving a system of inequalities, beware that the system might have no solutions as well. For example, this system has no solution because you can see the blue and pink do not intersect at all. And that means that the quantity x plus y cannot be both less than minus 1 and greater than 3. Another possibility is that the solution set of a set of inequalities could be unbounded. For example, if we have x plus y less than 3 and x plus 2y greater than 3, you see we get this region. It becomes unbounded because there is no boundary on here as we go up, even though there are boundaries here. The intersection of these two half-planes is an infinite wedge. There is a vertex, but the unbounded region could represent the feasible region or the solution set of those two qualities. Here's a problem. It's a word problem, and what you should really do is try to formulate this as a set of inequalities. And let's read it. The liquid portion of a diet is to provide at least 300 calories, 36 units of vitamin A, and 90 units of vitamin C daily. A cup of dietary drink X provides 60 calories, 12 units of vitamin A, and 10 units of vitamin B. A cup of dietary drink Y provides 60 calories, 6 units of vitamin A, and 30 units of vitamin C. Set up a system of linear inequalities that describe the minimum daily requirements for calories and vitamins. That is the number of cups that you should have. Pause the video and give this a go. Let's see how. So if you let X be the number of cups of dietary drink X, and let Y be the number of cups of dietary drink Y, to meet the daily minimum requirements you need to have for calories, 60X plus 60Y is bigger than or equal to 300. For vitamin A, 12X plus 6Y bigger than or equal to 36. And for vitamin C, 10X plus 30Y must be bigger than or equal to 90. And X has to be bigger than or equal to 0, and Y bigger than or equal to 0. The last two inequalities are included because X and Y cannot be negative. Now, if we graph all of this, we get this region, and you should make sure that you can come up with the corner points as well as the correct region. Now note, please, that any point inside the shaded region or on its boundary that meets the minimum daily requirements for calories and vitamins, and this is going to be called a feasible region. So for example, 3 cups of dietary drink X and 2 cups of dietary drink Y provide 300 calories, 48 units of vitamin A, and 90 units of vitamin C. And there are a lot of charts like this where you have inequalities, and this is an example of, here we have heart rate versus age, and we have the target zones for fat burning and high intensity workouts, and also for cool down. And fat burning happens in this region. And I'm sure you've all seen charts like this, but this is an example of such inequalities. Now we move on and we talk about, so what is linear programming? And we'll talk about how do you find a maximum or minimum of what we call an objective function subject to a system of constraints. And we will find what we call an optimal solution to real-world linear programming problems. And these usually involve their word problems. Okay. So let's begin discussing solving a linear programming problem. Many applications in business and economics involve a process called optimization, which is used to find such quantities as minimum cost, maximum profit, or minimum use of resources. In this section, we'll study an optimization strategy called linear programming. And we're going to talk about 2 dimensions here. We'll go into higher dimensions later in our course. A 2-dimensional linear programming problem consists of a linear objective function and a system of linear inequalities. This system of linear inequalities is called constraints. The objective function gives the quantity that is to be maximized or minimized, and the constraints determine what we call the set of feasible solutions over which we're trying to optimize. So for the function z equal ax plus by as our objective function, we take this subject to a set of constraints that determines the region in the figure, and this is called a feasible region. Every point in the region satisfies each constraint. So it's not clear how we go about finding the point that yields a minimum or maximum value of our z. But fortunately, it can be shown that this is where, when you find an optimal solution, it must occur at one of the vertices of the regions. This means that you can't find the optimal value by testing z at each of the vertices. This is the first LSA that I'm asking you to do. I'm asking you to write a proof that this is true for this two-dimensional case. And in fact, this is true not just in 2 dimensions, but this is true at higher dimensions, and we'll discuss this later. This is the theorem, and it says if a linear programming problem has an optimal solution, and that's the if part, then it must occur at a vertex of the set of feasible solutions. If a problem has more than one optimal solution, then at least one of them must occur at a vertex of the set of feasible solutions. In either case, the value of the objective function is unique. Kind of a satisfying result, actually. A linear programming problem can include, in the real world, hundreds or sometimes even thousands of variables. In this section, we'll solve ones that only involve 2 variables, and we'll move to solving slightly bigger problems as we go forward. And this is called the graphical method for solving linear programs in 2 dimensions, and this is outlined below. And so what you do is, first of all, you formulate the problem. You set up the objective function and all the constraints. But then you sketch the region corresponding to the system of constraints, including the non-negativity constraints if they apply. The points inside or on the boundary are called feasible solutions. Then you have to work to solve simultaneously these linear inequalities to find the vertices of the region. And then you test the objective function at each of the vertices and select the values of the variables that optimize the objective function. So for a bounded region, both a minimum and a maximum value will occur. For an unbounded region, if an optimal solution exists, then it will occur at a vertex. So here's a problem for you to consider. Find the maximum value of z equal 3x plus 2y, that is our objective function, subject to the constraints that are listed below. And so we have the non-negativity constraints. X plus 2y is less than or equal to 4, and x minus y is less than or equal to 1. Pause the video and please solve this. Let's see how you did. So you should have gotten this as your feasible region, these as your corner points. And when you substitute those into the objective function, you find that the solution is z equal 8. That is the optimal solution, and it is achieved at 2, 1. Again, your solution should have how you achieve the solution as well as what is the optimal value. Now, the graphic method for solving linear program works whether it's to be maximized or minimized in 2 dimensions. The steps are precisely the same. So after you've evaluated the objective function at the vertices, you choose either the largest or the smallest in order to solve this. In our little example, if we were minimizing z, it would happen at 0, 0, and you can see that 0, 0 again is a vertex of the point. Here's another problem. Find the maximum value of this function, z equal 4x plus 6y, subject to non-negativity constraints and additional constraints. Minus x plus y less than or equal to 11, x plus y less than or equal to 27, and 2x plus 5y less than or equal to 90. Please pause the video and give this a try. Let's see how you did. You should have come up with this as your feasible region, these as the corner points, and you evaluate each of those corner points in turn. You plug it into the objective function, and the maximum happens here. And so the maximum value of z is 132. And that happens when x is 15 and y is 12. Now here's a minimization problem. Find the minimum value of the objective function z equal 5x plus 7y, non-negativity constraints, and additional constraints, 2x plus 3y bigger than or equal to 6, 3x minus y less than or equal to 15, minus x plus y less than or equal to 4, and 2x plus 5y less than or equal to 27. Please pause the video and give this a try. Let's see how you did. you should end up with this as your feasible region, and those are the corner points that you get for the intersection, and you plug it into the objective function, and you're looking for the minimum. The minimum value is 14. This occurs when x is 0 and y is equal to 2. Now, when solving a linear programming problem, it's possible that the maximum or minimum occurs at different vertices as well. And these are alternate optima. And you can see in this case, when I change the objective function to be z equal 2x plus y, and having the same region, that the maximum happens at 2, 4, and also 5, 1. Sometimes you look at those alternate optima and you will figure out a way to discern between those, some additional factor in the problem. And in fact, this case, anything on that line between 2, 4, and 5, 1 will have the same value. Here's another problem. Find the maximum value of z equal 4x plus 2y subject to these constraints. Let's pause the video. Let's see how you did. So on this one, I guess and so let me go back to that. It's not letting me go back to that. Okay, here's the second LSA. This is a word problem. So the liquid portion of a diet is to provide at least 300 calories, 36 units of vitamin A, 90 units of vitamin C, and a cup of dietary drink A provides 60 calories, 12 units of vitamin A, and 10 units of vitamin C. A cup of the dietary drink Y provides 60 calories, 6 units of vitamin A, and 30 units of vitamin C. But now you have a cost, and that dietary drink X costs 12 cents per cup, and dietary drink Y costs 15 cents per cup. How many cups of each drink should be consumed each day to minimize the cost and still meet the daily requirements? More later as we move to larger LP problems. To be continued in sub. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself, because self-care is important, and of each other, because we're all in this together. God bless you all, and look forward to seeing you in class.